So let's do a simple example. Okay, we've got a 2-degree of freedom system here. It's relatively complicated. We have dampers. We've got springs connecting the mass to ground and to another mass. And here we notice that M2 also has a spring connecting it to ground. Okay, so there's it's a little bit more complicated than the systems we've seen before. But using the quick method from chapter 5, we can determine relatively straightforwardly the equation of motion. But we're not going to use that quick method. I'm going to use Lagrange's equation to get the same result. Just to show you how it works. Like I said, with linear systems, it's probably quicker to use the stuff we did in chapter 5. But for non-linear systems, you can't. You have to use the Lagrange's method. But this is just to demonstrate the process. And so, kinetic energy, well, we've got 2 masses. Okay, so we have 1/2 mv squared for both masses. Okay, so if I take the first mass, okay, m1, that moves in the motion x1. So 1/2 m1 x1 dot squared, okay, is going to be my kinetic energy for mass 1, and the same for mass 2. Okay, so that's relatively straightforward, nice and easy. For the kinetic potential energy, neglecting gravity, so there's no mgh's, it's all just the spring forces. So we've got 1/2 k1 x1 dot x1 squared, okay, which is the motion of x1, and so there's just that one spring. We've got 1/2 k2, and that's the relative motion between x1 and x2, okay. Now notice, because this is squared, it doesn't matter the order you put these in, because it will get us exactly the same result, so don't stress about that too much, okay. But it's the relative motion, it's not the individual motion. So we've got the relative motion, x1 minus x2 squared, okay, times by k2, and then obviously, as I said, there was a spring connecting mass 2 to ground, and so that's 1/2 k2 x2 squared. And then the next line down, I've just multiplied out that middle term, this one here. Okay, I've multiplied it out. Like I said, if that's the other way around, if you put x2 minus x1, you'll get exactly the same result down here. Doesn't really matter. And then what I've done is I've grouped them together in terms of, well, I've just, again, multiplied things out, and you can group them together how you see fit. So I can work out what R is. Okay, so I've got my 2 dampers in there. Damper 1 is related just to the motion of x1. Okay, so I've got 1/2 c1 x1 dot squared. And then the second damper was between the 2 masses. And so again, I've got the relative velocity of the 2 masses in there multiplied by 1/2 c2. And again, I multiply this out. Again, it doesn't matter the order because you get the same result. And then I've just written it out in long form there. So I can work out what L is. If I go back to my kinetic energy and potential energy, there's my kinetic energy, those 2 terms, and there's my potential energy, all those terms. Obviously, it's a minus sign in here, so obviously all those minuses have changed to pluses, and all the pluses have changed to minuses. So this is where we start the process of differentiation. Well, I'll set up the generalized coordinates first. x1 is q1, q2 is x2, and then obviously the big ones will be any forces that are being applied. I've not defined the forces in this problem. I've simply called them F1 and F2. So let's go back to there's L. Okay. The first process is to find dl over dx dot. Okay, well, it's quite straightforward because all the terms, this one, this one, this one, this one, and this one, do not contain x dot. Okay, so they're all assumed to be constant. You take the derivative of a constant, you get 0. They all disappear. We're dealing with q1, okay, or x1, so obviously this one is also a constant, so that disappears. So the only term that we have to deal with when we're differentiating with respect to x1 dot is this first term. If you take the derivative of this, obviously the 2 comes down in front, 2 times a half becomes 1, you end up with m1 x1 dot, which is what we get. Okay? Anything that doesn't have x1 dot in it is a constant, it disappears. So you just have to deal with the term that's got x1 dot in it. Okay? And you take the straightforward derivative. There's no, you don't have to use the product rule or anything like that. It's just the straightforward derivative of x1 dot. Now then, when you take the time derivative, well, there's something in here that's going to vary with respect to time, and that is x. Okay, we've got x, and that is x dot even. And obviously, if you take the time derivative of x dot, you get x double dot. So there's our first term. Okay, d by dt of dl over dx1 dot gives me mx1 double dot. Okay. Okay, now we look at x1 on its own. Well, if I go back to my L, there's my L. I'm looking for x1 now. This is a constant, drops to 0. This is a constant, drops to 0. I've got to deal with this term. There's an x1 here. I've got to deal with this term. There's an x1 here. And I've got to deal with this one. There's an x1 here. That's x2. That's x2. They're both constants. They disappear. So I've got 3 terms to look forward to. Okay, take the derivative of this. Obviously, the 2 comes down. This becomes k1 x1. This one, the q2 comes down. This becomes k2 x1. And this one, obviously, I've got some constant multiplied by x1. If I take the derivative with respect to x1, the x1 disappears. I just end up with the constant. And so I end up with this, okay? So this, if you remember, was minus 1/2 k1 x1 squared. You take the derivative with respect to x1, you get the 2 coming down. 2 times 1/2 is 1. Okay, so you end up with 1 times k1 x1. Again, that was the same process here. And here we had k2 x1 x2. You take the derivative of that with respect to x1, the x1 disappears, you just end up with the constant k2 x2. Then lastly, for x1 dot with r, okay, so this, you don't deal with L this time, you just look at your r, and again, the same process applies, the 2's come down, and you end up getting rid of the halves, and getting rid of those x squared, x dot squares and stuff. You end up with this equation. So then you apply Lagrange's equation. There's Lagrange's equation. Like I said, our force is at Q1, and we end up with this. Okay, so here's our, this is that term. If you remember, that turned into mx double dot. This is our L, dl over dx term, which is in here, but that's a minus sign. So these are going to turn into a plus, and then over here we've got our damping term. And like I said, if you rearrange it, sorting out the terms multiplied by x1 double dot, x1 dot, x2 dot, x1 and x2, then you get this equation. You can repeat the process for I equals 2. Okay, so there we go. Again, with L, you take it with respect to x2. Okay, you then take the time derivative, so the x2 in here turns into x2 double dot. You take the derivative of L with respect to x2. Okay, again, you go through the process, you get this. And then if you take the derivative with respect to x2 dot, sorry, the derivative of r with respect to x2 dot, you end up getting those 2 terms. And again, you can group them together, right, put them into Lagrange's equation, and you get that second line or third line down there. Now, if I put those 2 together, there's the 2 equations. What we can do is we can write those equations in matrix form. Okay, because we've got x1s and x2s, they're coupled equations of motion, but because of the fact they're linear, we can actually write them in terms of matrix form, and you end up getting this, which is what you get from the quick method. We've got the masses down the diagonal, okay, everything else is 0, times by x1 dot, x2 double dot. There's those 2 terms there. Okay, with the damping, the diagonal, we've got the dampers between, we take mass 1, okay, we take the dampers between ground and another mass. Well, there was one damper between ground, and there was one between the masses, so C1 plus C2. Mass 2 only had the damper connecting it to mass 1, so that's my C2 in here. And then obviously between the masses, we've got minus C1, minus C2. Okay, and that's multiplied by the velocity. And then the same thing with the springs. We had, for mass 1, we had the spring K1 connecting it to ground, and spring K2 connecting it to the other mass. For mass 2, we had spring K2 connecting it to mass 1, and K3 connecting that mass to ground. Okay, so there's those diagonals. And between the springs, we had K2, so we've got minus K2 on the off diagonals, multiplied by your displacement equals your forcing function. So there, like I said, we've gone through the same process, we've gone through Lagrange's equation to find these equations here, and we end up with the same thing that we get from the Newton's second law, the quick method. Okay, so the same process, sorry, the same result from a different process. Now, like I said, I wouldn't recommend that with a linear system you use this process because we've already learnt the quick method and we can jump straight from the picture to this. Okay, so I wouldn't recommend it for a linear process because you could go straight to this process in a relatively quick fashion.